At the University of Tasmania, Donna Roberts and her team are searching for signs of ocean acidification.
That's a good one. Look at that.
This is what she's looking for. Tiny planktonic snails called pteropods. With shells the size of sand grains, they float using their foot like a wing and catch plankton in nets made of mucus.
There are millions and billions of tonnes of pteropods in the Southern Ocean, and in some regions, particularly the Ross Sea area, there is more pteropods per cubic metre than krill. What I do is I'll pick up an individual shell, have to use a wet paintbrush.
No, and steady hands.
Oh, yeah.
Should I tell you if I'm about to sneeze?
Yes, you should. These guys are worth hundreds of thousands of dollars to collect. Pteropods have a really, really fragile shell. All shells are made out of calcium carbonate, but not all calcium carbonate is created equal. There's two types, and the scientific names are calcite and aragonite.
When CO2 dissolves, it reacts with water to form carbonic acid and carbonate ions, which decreases the pH. Aragonite is more soluble, so any change in pH will affect the growth of aragonite shells first.
Now, aragonite is actually in the shells of pteropods and in corals. So corals and pteropods are going to be at risk first if the ocean health and the ocean chemistry changes, and it's changing because we're putting carbon dioxide into the water. We weigh the shells individually. Each shell will be about 15 micrograms.
15 millionths of a gram?
Yes. I've probably weighed a couple of 100,000 shells. We're actually comparing shells from 10 years ago to shells from today, and what we find is that the shells of today are 35% smaller and more fragile than they are 10 years ago.
That means the pteropods of the Southern Ocean and the food chains they underpin may be living on borrowed time. Donna can calculate the CO2 levels when they'll basically run out of shell.
The tipping point for pteropods in the Southern Ocean is 450 parts per million, and we're currently at 388, so we're heading there rapidly, and we think from models that we're going to get there in about the winter of 2030.
From the minutiae of tiny snails to the world's most powerful currents, there are clear signs the Southern Ocean is shifting in response to the changing atmosphere.
The real challenge then is to be able to design very efficient programs that can measure rates of change. But we don't have enough time series from enough areas around Antarctica to say here is how the Southern Ocean is changing as a whole.
To achieve that, Andrew Constable is organising a targeted research program called the Southern Ocean Sentinel.
What we're aiming to do with the Southern Ocean Sentinel is to be able to work out what should we measure that will correctly forecast the changes that are going to happen in decades to come. And at the moment, we don't know how to do that.
All this needs big science on an unprecedented scale. Over a vast area, in some of the most hostile conditions on Earth, scientists have to gather enough data to forecast climate change tipping points. And who will listen if they do?
One of the difficulties that I have with the debate at the moment is that it's leading us along the path of reacting to signals of change. Waiting for a signal for change means that we're likely to be too late. So can we come up with some way of signalling future change and therefore be better equipped to adapt to the future rather than waiting?
If you take a bottle of water from the Antarctic and you look at it under a microscope, it's just beautiful, and there would be more things out there than people are not aware of. And I hope that people actually learn what a pteropod is and actually learn to care for it to save the pteropods. Yeah.